Welcome to this webinar. Before we begin the presentation, I want to provide you with a few housekeeping items. On your screen, you will see a taskbar with icons. Each icon is assigned to a particular element of today's webinar. After the webinar is over, please take our survey to tell us how we've done. Throughout the presentation, you can network with others or submit questions to the speakers in the box next to the slides. Download resources from the folder icon. Today's event is being recorded and archived and will be available within 24 hours. For on-demand questions or comments, send us an email by clicking Email Us. If you experience any technical issues today, please refresh your browser by hitting F5 for a PC or Command-R for Macs, or email webinars@bmpmedia.com for one-on-one support. And now I'm excited to turn it over to today's moderator.
Good afternoon, everyone, and welcome to this webinar, Use of an Expert System for Interpreting Pyrolysis-GC data for Synthetic Paint Media. This event, brought to you by Paint and Coatings Industry Magazine, is sponsored by Frontier Lab. I'm your moderator, Kristen Johansson, editor of PCI. Thanks for joining us. Today's presenters are Rogine Belgane, Dr. Terry Ramis, and Dr. Michael Schilling. Rogine Belgane is the Technical and Marketing Director at Frontier Laboratories North America. Rogine graduated from the University of Houston with a Bachelor of Science in Chemistry. She also holds an MBA degree concentrating in strategic marketing from the University of Houston, Victoria. As a former user for more than 5 years, Rogine joined Frontier Laboratories in May of 2017. Terry Ramis is a scientist and operates the North American Technology Center for Frontier Laboratories. Terry has more than 35 years of experience in a wide variety of companies and markets with emphasis on analytical chemistry. Terry holds a BS from the University of California, Davis, and a PhD in analytical chemistry from Oregon State University. Michael Schilling, who began his career at the Getty Conservation Institute in 1983, is a senior scientist and head of the Materials Characterization Group. Given the prevalence of organic materials in works of art, his group studies a broad range of traditional and contemporary museum objects and participates in field projects at World Heritage Sites. Michael earned his BS and MS degrees in chemistry from California State Polytechnic University, Pomona. Don't forget to submit your questions, and later in the program, our presenters will address as many of them as possible. Today's event is being recorded and archived at pcimag.com. And now I'm excited to turn it over to today's first presenter, Rogine.
All right, thank you, Kristen. So here's our agenda for today, who we are. Then we start with the fundamentals of pyrolysis. After that, we go into details of the multi-mode pyrolyzer, its operational modes, and the method map. We will also discuss the sample preparation and the system configuration. And then we'll have an application for characterization of paint by Dr. Michael Schilling. So let's start with a brief history of Frontier Laboratories. Frontier Labs was founded in 1991 by Dr. Chusan. Chusan, with the support of polymer scientists at Nagoya University in Japan, developed a pyrolyzer based on a vertical microfurnace design. And we will discuss the characteristic of microfurnace design in a few minutes. We are a global manufacturer, and our main products are a series of pyrolyzers, such as the multi-shot and a single-shot pyrolyzer, rapid screening reactors for catalyst analysis, and also a line of ultra-alloy stainless steel capillary columns. As you could see from here, we have different office locations around the world, and our North American Technology Center is located in Antioch, California. Today, we will mainly focus on the multi-shot pyrolyzer and how it can expand your sample analysis capabilities in paint industry. A little bit about Quantum Analytics, that are a value-added distributor for Frontier Laboratories. They have been in business for about 30 years. Their headquarters is located in Foster City, California, and they have a technology center in Houston, Texas. They also offer financing programs as well as the technical application support. So let's start with fundamental of pyrolysis. What is pyrolysis? Pyrolysis is a thermochemical decomposition of organic compounds at elevated temperatures without the participation of oxygen. Typically, this technique uses an inert gas such as helium. So in this technique, a sufficient amount of heat breaks down the organic bonds of the complex mixture into a smaller and more stable molecule called the pyrolate. The pyrolytes then form, and their relative intensity provide insight into the nature of the original composition. But it is very important to mention that applying the sufficient amount of heat and identifying programming the pyrolyzer furnace are two critical factors in pyrolysis technique. So as we go more into details, you'll find out how to identify that sufficient amount of heat so you're not really overheating or underheating your samples. So now let's discuss how you can expand the material characterization capabilities using Pyrolysis-GC. As you could see here, substances at ambient temperature exist as gas, liquid, or solids, mostly depending on their molecular weight. Compounds that are soluble in solvents can be analyzed by GC or LC. Of these compounds, as you could see here, about 30% can be analyzed by GC, about 80 to 85% by LC, of course using the proper solvent. So there are also some solids that are insoluble and cannot be analyzed by LC, LCMS, GC, or GCMS. But these insoluble compounds can be analyzed by Pyrolysis-GC, and that's really where the PyGC or PyGCMS comes in place and expands the capabilities of your GCMS. So using this technique, there is no need for any solvent extraction or sample preparation prior to your analysis. You could inject solid sample as is without any solvent. So as you could see now, the entire range of organic compounds from gases to solids can be analyzed using this technique. And that's really how the multi-mode pyrolyzer can expand your GCMS capabilities. Usually polymers can go through three main degradation mechanisms. Of course, depending on the mixture, the polymer might go through one or a combination of random scission, depolymerization, or a side group elimination. So for random scission, polyolefins such as polyethylene, polypropylene, and polybutylene are very good examples. So in this case, the CC bonds break to produce fragment patterns of increasing oligomer sizes. In a depolymerization mechanism, polystyrene can be a good example, and in this case, the polymer thermally degrades into its monomeric fragmentation. So for polystyrene, you'll see a styrene monomer, dimer, and a trimer. In a side group elimination, PVC, polyvinyl chloride, can be a good example. In this case, the side group, that is Cl, and is attached to the side of the polymer chain, breaks before the CC bond breaks. So the Cl removes the hydrogen from the polymer chain. Some unsaturated polyenes plus the HCl will form. Then these polyenes form aromatic compounds such as benzene and naphthalene. So let's see how we can analyze these compounds and fragmentation in Pyrolysis-GC. As shown here, S-Search is a search engine that has 4 unique interpretation libraries. So you can identify additives, volatiles, lighter components, as well as oligomers, heavier, and polymeric compounds. S-Search also allows you to create your own user library, so you could perform contamination analysis, comparison, and also failure analysis. S-Search has other features like the ability to overlay different chromatograms, extract different amorphous Z ions, and also performing integrated sum analysis, which in this case, the S-Search engine can actually integrate the whole chromatogram, make an average mass spectrum, and then identify the corresponding polymer. This book is used along with the S-Search and the MS libraries as a reference. The book has pyrograms, EGA thermograms, and MS data of major pyrolytes for many polymers. As you could see, it also has detailed information about the peak assignment tables and the EGA thermogram of each polymer. So now let's take a look at an example from the book. So this is an example that shows the flash pyrolysis or PyGCMS of polystyrene. And as I noted, polystyrene goes through a depolymerization mechanism. So you're able to see the starting monomer, dimer, and also the trimer. So as shown here from the book, you can see the pyrogram on the top from the left side, and then the assignment of main peaks, as well as the average mass spectrum that is shown on the top right side, and the EGA thermogram. And also you could see some of the major pyrolate or fragmentation of the polymer. Okay, now let's start talking about the multi-mode pyrolyzer and how it works. So as the name says, using the multi-mode pyrolyzer, multiple analyses can be performed on a single sample. This is actually one of the advantages of our pyrolyzer, where the furnace can be used for other analytical techniques in addition to flash pyrolysis. So the multi-mode pyrolyzer can be used for both thermal desorption and pyrolysis by identifying the volatiles, additives, lighter components, also as well as oligomers, heavier and polymeric compounds. So you can perform evolved gas analysis, EGA, thermal desorption, flash pyrolysis, reactive pyrolysis, and even hard cutting technique. And we'll discuss each of these techniques in a few minutes. So now that we mentioned you have multiple analysis using the multi-mode pyrolyzer, where would you start? So we developed a series of techniques as a method map to chemically characterize samples using this technique. So in this technique that is virtually applicable for any organic compound, from volatiles to high molecular weight polymers, the first step is to perform evolved gas analysis. Then EGA, evolved gas analysis, is used to determine the next step and guide you what to do next. For example, it will show if a thermal desorption step is needed or if a multiple hard cutting step is required. Also, EGA shows the optimal and proper temperature for flash pyrolysis to analyze the polymers, so you're not overheating or underheating your samples. So as we mentioned, EGA is the first step. To perform the EGA, as shown here at the bottom in the figure, a short and deactivated tube is used that connects the injection port to the MS. So in this technique, the sample is dropped into the furnace, which is relatively at a low temperature. In this case, we're starting from 100 degrees Celsius. Then the furnace is programmed to a much higher temperature. In this example, it's 700. And then compounds evolve from the sample as the temperature increases. So you obtain a detector response versus furnace temperature on the right-hand side. We call that an EGA thermogram. So now using your F-search, you can start analyzing your EGA and even perform more detailed analysis on your sample. That will be the next step. So now to further analyze your sample, the second step is to perform any of these methods here or a combination of them. So you could perform thermal desorption. This technique mostly is for analyzing additives and volatiles, but the key point here is that the additives and volatiles are thermally extracted from the mixture. So instead of performing any solvent extraction or sample preparation, you actually thermally extract the additives from the mixture or the polymers. Or you could also perform flash pyrolysis. We call flash pyrolysis a single-shot GCMS as well, and that's been shown on the left-hand side at the bottom. So in a flash pyrolysis, that is a fundamental technique for analyzing your polymers. Most of the time, temperature, say like 600 or 700 C, to break down your polymer or the heavier components. Then you will obtain a GCMS chromatogram. So you're performing one or single analysis on your sample. And that chromatogram that you will obtain is the combination of additives, lighters, and the polymers. But as we discussed, if you have some additives and if you want to identify them, now you could do a double-shot GCMS. We call this a double shot shown in the middle because this is two analyses on one single sample. First, you thermally extract the GCMS chromatogram. We call it a thermal desorption chromatogram. And then the second shot or the second analysis is to perform a flash pyrolysis. And you obtain a separate GCMS chromatogram. We call it a pyrogram to identify the heavier and the polymeric components. You can also see hard-cutting EGA-MS on the right-hand side, and we'll talk about this in a few minutes, but this is A very powerful technique. We use this in our laboratory for deformulation and reverse engineering. It's a multiple-step thermal desorption and multiple-step flash pyrolysis. And we'll talk about that in a few minutes. So let's focus on flash pyrolysis. As we mentioned, we first run EGA that is shown on a top figure as the EGA thermogram. So from that EGA, you could see the optimal temperature. Now you want to perform your flash pyrolysis is at 600 degrees Celsius. So to perform flash pyrolysis, you have to switch the EGA tube to a separation column, and that is shown on the left-hand side. You'll do that switching of the columns by an accessory called GCMS vent-free adapter. This is something that allows you to switch the columns from EGA to separation column or vice versa without actually having to vent your MS and waiting for it to be pumped down. So it saves a lot of time and add efficiency in your laboratory. Then you program your furnace at 600 C and you obtain a pyrogram. That is a combination of additives and polymers. Again, this is called single shot or the flash pyrolysis. Now we discussed about thermal extraction. So first step is to run your evolved gas analysis. In this case, it was done from 100 to 720 degrees per minute. Notice the EGA tube and keeping the GC oven isothermal. Then you'll obtain an EGA, a thermogram. The x-axis is your temperature and the retention time, and the y-axis is your intensity and concentration. So now to analyze the first peak or the hump from your EGA thermogram, you have to switch the EGA tube to a separation column. That is done very quickly and easily from the vent-free GCMS adapter. And then you program your furnace from 100 to 300, and you'll obtain a TD chromatogram. So now you are thermally extracting all those additives and volatiles from the mixture. And now to analyze the second peak from your EGA, this time you'll do the second analysis, and we call this a flash pyrolysis because you heat up your furnace high temperature around 600 C. And we call this a double shot because it's pyrolysis. So quickly going over the hard cutting, if you have an EGA thermogram that is shown on the right top side, you could see that you have more than 2 peaks. So there are zone A, B, C, D, and E. So hard cutting allows you to slice your EGA thermogram into a smaller temperature zone, such that you program your furnace for zone A from 40 to 120, zone B 120 to 220, all the way to zone E, and you obtain separate GCMS chromatograph run for each zone. We use selective sampler as an accessory, and as you could see, selective sampler allows you to selectively pick and choose which one of these zones you want to send to your GC. For example, if you do not want to obtain the GCMS run for zone C, you'll just do sampling off using your selective sampler, and you will not obtain zone C GCMS run. Sample preparation is very straightforward and efficient, depending on your sample time. If it's a liquid or solid, semi-liquid, semi-solid, you just use an appropriate sampling tool, place it into an equal cup, and it's good to go. No need for any solvent extraction or sample preparation because, again, we are performing a thermal extraction using this technique. This is the system configuration for Pyrolysis GCMS. A couple of key points I like to point out here is that how number 2, that is the actual furnace, that is the pyrolyzer, is directly connected to your GC. So there is no transfer line. There is no chance of evaporation or degradation of some of the lighter components prior to analysis. You could also see number 1, that is the auto shot sampler, and that automates the process. We talked about number 6, the vent-free GCMS adapter. I also want to point out quickly about number 4, the microjet chirotrap. So this accessory is at the head of your GC column, uses liquid nitrogen to trap and focus all those volatiles and lighter components. So if you are working and trying to analyze lighter additives and lighter components, that will be something that you want to have at the head of your GC column. Last slide I have is just going over how the pyrolyzer functions. So the sample introduction is nearly instantaneous. The sample is placed into a sample cup. We call that an echo cup, and is held at near ambient temperature in helium. The microfurnace is then preheated to the desired temperature, for example, 600 C. But that temperature is precisely measured with a thermocouple sensor. The sample cup then drops into the quartz pyrolysis, where the sample is pyrolyzed in less than 20 milliseconds. The pyrolytes are then flipped onto your GC column for detection by the MS. So using this technique, you are performing a continuous mode pyrolysis, where your sample is held at an ambient temperature while the furnace is preheated. So your sample does not get exposed to any heat prior to the analysis. As a result, there won't be any degradation or evaporation of the lighter components prior to your analysis. So that's all I had for today. Now I would like to hand it to Dr. Schilling for his application.
Thank you, Rojin. That was very interesting. I learned a lot from your lecture, and I think we all saw why PyGCMS is such a powerful tool for characterizing polymers. In case you haven't heard of the Getty Conservation Institute, I'll give you a little background on us before moving into the rest of the talk. So I'm a senior scientist at the GCI in Los Angeles, working in the field of cultural heritage preservation. There are a relatively small number of professionals at organizations around the world that do this kind of work. One of the things that we do then is conduct research to study and preserve museum collections, historic buildings, sites, and monuments. Chemists like me working in this field often address questions like, what materials did the artist use to make this object? How have those materials changed over time? What materials and processes might help preserve this object? And as Rojin mentioned, PyGCMS is an excellent tool to answer some of these questions. One thing that it involves is taking samples from works of art. That's always a nerve-wracking process. We let the conservators do that quite often because they're skilled at taking small samples. And we just get usually one small sample to give us all that information. And so we have to make our analysis count. And so that's, again, why we like to use the Frontier Pyrolyzer. It gives very reproducible sample results for us. And again, the questions that we have may be similar to some of the questions that scientists in the paint and coatings industry have. So we do have this commonality in trying to tell people that work with us, our clients, what is this? What is this material? So a small group of us got together to help develop tools to answer these questions. And I'll be presenting our collaborative work then. So the typical process to interpret a pyrogram is you identify compounds in the pyrograms using some type of mass spectral search program. Sometimes you use retention index. Second step then is relating those marker compounds to the materials that form them. So marker compounds are generated in the pyrolyzer either by evaporation, desorption, or pyrolysis. Marker compounds are characteristic of a material, and they're present either in the original material or they're formed by aging. And again, the objects that we work on often are quite old, and so sometimes the compositions have changed quite a lot over time. So then we confirm that a material is present in a sample if its associated set of marker compounds is detected. Some compounds are formed by many different categories of materials, so they have limited diagnostic value, things like toluene, of course, not specific to any one type of material. So we've been doing PyGCMS here at the GCI for about 10 or 12 years, and we were reluctant to get involved in it at first because of the need to have a really deep understanding of the relationship between materials and their marker compounds. It takes years of practice. And so again, some of you may be reluctant to try PyGCMS as an analytical tool. You may be feeling the way we did years ago. I don't know enough to interpret the data. I'm looking at the pyrogram and I'm just confused by it. There are so many books and articles to read, and to try and remember all that information or put it into a system that you can retrieve it easily is challenging. And again, that was pretty much me there, nibbling on my fingers, looking at my first 100 pyrograms, wondering what that material might be. So again, there are a small number of us that developed this system. We call it ESCAPE. It's an expert system for characterization using two software tools, AMDIS and Excel. And we made it to evaluate PyGCMS data from natural products and synthetic paint media that are used in cultural heritage. But again, there are extensions to the broader field of paint and coatings. So in this system, we have about 170 person-years of practical experience in materials characterization using PyGCMS. And the experts that I list there are the ones who really worked side by side with us to fully develop the system and expand our small database at first into something much larger and more comprehensive. Henk van Keulen, working at the Netherlands Cultural Heritage Agency, is an expert in natural and synthetic material identification. Natalie Balkar, working at the Center for Research and Restoration of Museums of France, she's an expert in synthetic paint media and plastics identification. Jenny Poulin, working at the Getty Conservation Institute, provided expert knowledge on natural resins and dye stuffs. My boss, Tom Lerner, did a PhD on characterizing synthetic paint media with PyGCMS. I learned a lot from his work. Arlen Higginbotham is a furniture conservator at the J. Paul Getty Museum, located on our same campus, and he and I worked together to put together the basics of the system. And Mike Zalewski had the patience to teach me AMDIS, and he is a scientist from Agilent who also volunteers at the Winterthur Museum in Delaware. So this is the core group of people who got together to develop ESCAPE. It's a two-step process. The first is to process the PyGCMS data with AMDIS. Now, AMDIS is a complicated program to explain in a short webinar, but I'm just going to hit on the highlights of what it does. You can find out much more from the NIST website. There's an excellent user's manual. It's long, but it's very thorough and detailed, so you can get all the extra information you need to know from it. But basically, the program is freeware. It was developed by researchers at NIST to identify chemical weapons for forensic examinations. So it deconvolutes GCMS data. In essence, it's a type of background subtraction where ions are bundled together for each peak in a chromatogram. The math is explained in the manual. But basically, once the background is subtracted, peaks are identified in the chromatogram, and then the peaks are identified by matching their deconvoluted mass spectra to a user library in the AMDIS program. It's not the NIST library, it's a specialized AMDIS user library. Retention index is an excellent extra characterization factor to exclude false matches. So if you're interested in identifying hydrocarbons, their mass spectra tend to look very similar once the molecular weight gets quite high. So retention index is an essential bit of information to differentiate them, the different homologous series members. So then AMDIS measures the peak areas of those compounds and retention indices, and it tabulates all the information on that sample data into an AMDIS report. So right now, there are 1,455 marker compounds in our AMDIS ESCAPE library. So you can see it's quite large, but focused again on synthetic paint media and natural products. So when you run AMDIS, you get a window that looks like this, and it gives you a list of target compounds on the right, and components are peaks that do not match a library spectrum in the AMDIS user library. So that's what the window looks like after you've run AMDIS. It has a chromatogram on the top. It has an extracted spectrum or deconvoluted spectrum from one of the components in the middle, and then the library matches on the bottom. And next to the name of the compound in the bottom window is the match factor, that's MF, 98%, so it's a 98% probability that that extracted spectrum in the middle matches the library spectrum on the bottom. You also see in the lower corner RI minus RI lib, and that relates to how close the measured retention index of the compound is to the known retention index for that marker compound. Okay, I'm going to show you a video of how you use AMDIS and how rapidly it runs. This is the window before you process AMDIS. You click on the Run button. It takes just a few seconds to give you all the information on the components. So all of the peaks are components, and the components that match a library spectrum are targets. The targets are listed in the right. You can scroll through the results by clicking on the target compound list on the right. You can also click on the small t's above the target compounds. That helps you to check on the match qualities. And then once you're satisfied with the results, you can generate the report from within AMDIS. We give the file name a standard name, amdisreport.test. We put it on the desktop, and we write to that file. And we do that so that we can find it easily for step number 2. This is how you use AMDIS. It has to be set up to do this, and to set it up, you have to know a little bit about the libraries and how they're structured, and the parameters are fairly easy to set up, again, with a little bit of training. So the second step then is to identify materials using the ESCAPE Excel report template. And that colorful bar that you see is our different worksheets within the Excel report. For those of you who have used Excel, each workbook has many worksheets in it. We've named them and color-coded them depending on the function that they provide. Okay? So all you have to do is paste that AMDIS report into the Excel report template. You paste it into the sample worksheet. That's the one that's highlighted right now in that colorful bar on the bottom. So the equations that we put into the report template sort the marker compounds by the library entry number. And then we use expert knowledge to assign the marker compounds to the material that formed it. And I listed just a few of the important Excel functions that we had to learn about. We're not programmers. We learned about these functions from just Google searching them. And so you can do the same thing. If you're interested in this type of data evaluation, you'd have to get familiar with these functions as well. So after the equations sort the marker compounds, they're sorted into different categories. So you see just a few of the categories here. Additives and acrylics are the main two. So they're sorted by the type of material or the class of compounds, class of materials. So then the last step is the marker compound data is presented as graphs and tables that summarize the results and help the user then to identify the materials. These are some of the graphs that are produced. These are bar graphs for acrylic type paint media. And there are two types of acrylic paint media that are evaluated here. Winsor Newton on the top. It's an N-butyl methacrylate, methyl methacrylate copolymer. Liquitex is on the bottom. It's an ethyl acrylate, methyl methacrylate copolymer. And the pie charts on the right show the overall distribution of all of those different types of paint media or products that are in the sample. You can see that both of these samples are 100% acrylic polymer. So you can use these bar graphs to easily differentiate the types of paint media. What we've done in the colorful bar graph, colorful bars on the right, is we've bundled together all of the ethyl acrylate markers if they are present as sesquimers, dimers, and trimers. And Regine mentioned the dimers and trimers before in her talk. So that's how we got the colorful bars on the right So we have the comonomers, and then we have bundled together the sesquimers, dimers, and trimers. So for vinyl paints, the bar graph looks quite different, and the distribution, the pie chart, shows the distribution of the marker compounds, and again, it's quite different than the acrylic. There are two bar graphs that are helpful for differentiating vinyl paints. That would be the bar graph on the left that shows the main categories, and then the aromatic compounds that form from side chain elimination are listed on the right. And so when there's expert knowledge that helps the user differentiate paint media, it would appear in some kind of highlighted text like that yellow note that's on the bottom. Vinyl paints have acetic acid and plasticizers. Styrene may be present in modified acrylics. So that extra bit of information might be the key that a user would need to differentiate vinyl paints from other type of paint media. So now I'm going to show you how to obtain the chromatogram that you need from AMDIS, and then we're going to go ahead and import that into our Excel template. Okay, so this is what the template looks like when you open it up. This is the overview page. It's kind of like a summary report of what might be in the sample. There are 6 categories of paint media. I only show 4 here just for clarity. First thing we're going to do is open that chromatogram file that we just created. And that AMDIS creates that for you. So it's a nice way to archive your tick. You see that is a list of the ions that are measured, the scan number, and the peak area. We're going to copy that. We're going to paste that into the tick page of the Excel report. Now we'll go to the overview, and you can see the chromatogram pop up automatically. All right? So now the next thing we're going to do, go to the sample page. We're going to open the AMDIS report that we just created on our desktop. We're going to copy that entire file. And then we're going to paste that into the sample worksheet in the Excel report. Now we'll look at the overview, and we'll see how the formatted graphs have changed. See all of the graphs pop up automatically. So it saved me a lot of trouble as a user. I don't have to go through each peak one at a time to figure out what they are and what material they're assigned to. The worksheet does it for me automatically. So the more bars there are in a bar graph, the more likely it is that that material is present. You can see there's only 1 bar present for alkyd. So we're going to type no in. The alkyd is not present in that sample. That makes the bar graph go away, and it also updates the pie chart on the left. Now we're going to look at the vinyl page. Looks like there may be a tiny bit of vinyl, so let's look to see if all of the marker compounds are there. Not all of the blue bars are there. They're the polycyclic aromatics that should be present if there was vinyl paint. So we're going to say no, there's no vinyl in that. And that's our final result. It's an acrylic paint. These are the additives that are present in the additive page. Just a small amount of those, less than 1%. And now we're going to zoom in a little bit so you can see it a little more clearly, the 2 main results. The pie chart that shows 99% acrylic, 1% additive, and then the type of acrylic, the ethyl acrylate, methyl methacrylate copolymer. So that's the way you would use ESCAPE then to evaluate the data. So to sum up then, ESCAPE is a powerful, easy-to-use tool for comprehensive data interpretation that can benefit users of PyGCMS regardless of their level of experience. So Hank and I have taught workshops on using ESCAPE, and even researchers that had just started using PyGCMS were able to differentiate different types of paint media in the tiny samples that we get from cultural heritage. The main thing that it does is it systematizes knowledge about material identification in a practical and effective way. You don't need piles of articles and books on your desk. All of that information, all of your experience, and all of the experience of the other users are put into the system. The system works because the pyrograms that come out of Frontier microfurnace pyrolyzers are very reproducible. So that means that the data are amenable to processing tools like ESCAPE. And again, newcomers have more confidence in their ability to interpret data if they have tools like this. The range of materials that can be identified by ESCAPE depends on the breadth of expert knowledge in the system. Right now, it's focused on cultural heritage applications, but we've all learned that the sharing of expert knowledge within a cooperative research community mutually benefits all users. So that's why some of us who've been doing PyGCMS longer are happy to share our knowledge with our own colleagues here and also colleagues in our partner labs around the world, because the more knowledge that we share, the more each of us can do in our own work. One of the reasons I'm reaching out to the paint chemists today is we hope to make connections with some of you to broaden the present capabilities of ESCAPE. And we've also done some presentations for forensic scientists. We've shown them how ESCAPE can be used to present the PyGCMS data of paint media, and they were interested in the bar graph format. And they thought that juries would be able to better understand the analytical results if they were presented in that way.
Great. Thank you so much, both Rogine and Michael, for a great presentation. We now have some time to address some of the questions that have been submitted throughout the program. The first question, Michael, is for you. Is there or are there any internal standards recommended for quantitative single-shot 600°C pyrolysis of acrylic copolymers, or are external standards preferred?
What I've presented are peak area amounts, so we don't do quantitative analysis. That would be much more challenging.
Okay,
so they're peak areas.
Okay, next question is also for you. Can I use this method to identify a solid contamination on finishing film paint?
Yes, if you and your colleagues have experience in this kind of analysis, you can develop your own ESCAPE database and AMDIS library that reflects the composition of the types of materials that you have. One nice thing that AMDIS does is it allows you to link right to NIST, and you can do automated NIST searches from within ESCAPE. So if the compounds aren't in your own library, you might be able to find them in NIST.
Okay, the next question is for Rogine. Why choose to do flash pyrolysis over double shot? Are there materials that do better in one technique over the other, or specific application spaces where it matters more?
Okay, so let me actually go back and have that slide on while I'm explaining this, so it will be more, okay. Okay, so as we talked, flash pyrolysis is a single-shot analysis, and you could see that on the left-hand side at the bottom. So in this technique, your pyrolyzer furnace will be programmed at a high temperature in a single temperature, for example, 600 C. So 1 GCMS chromatogram is obtained using the single-shot analysis where all the organic compounds are detected using the MS. So you get 1 GCMS chromatogram that is a combination of additives, volatiles, and all the polymeric components. So flash pyrolysis or single shot is the fundamental technique for polymer analysis. But whenever you run, especially from your EGA, whenever you can see that your sample is a mixture of additives and polymers or copolymer, then you want to perform, of course, EGA first, but then a double shot might be used. Because in this case, you are separating and thermally extracting all those lighter and additive components from your heavier compounds in the sample. So you obtain 2 GCMS chromatogram. The first shot, as we talked, as shown here, is the thermal desorption chromatogram that detects all those volatiles, lighter components, and additives. And then the second shot, or the second analysis, where you actually set your furnace at a higher temperature, it identifies the heavier and polymeric compounds. So instead of having one chromatogram for single shot for additives and polymer, whenever you perform a double shot analysis, you thermally extract the additives and you actually obtain two separate GCMS1. Double shot also, as I mentioned, eliminates the need for any solvent extraction or sample preparation prior to your analysis. One additional note I like to have here is, and also we talked about this a little bit on the right-hand side about the hard cutting technique, that if your EGA contains more than 2 peaks, or if you want to perform a reverse engineering and deformulation, you could perform hard cutting EGA, where you actually thermally slice your EGA thermogram into different temperature zones. And you actually can perform up to 8 zones on one single sample. So you obtain separate GCMS1 for each zone from your EGA.
Okay, great, thank you. The next question is for Michael. What is the minimum and maximum sample size needed for a positive ID?
Typically, we analyze anything from about 10 micrograms up to about 100. It depends on the amount of organic material that's in the sample. Since what I've shown you relates mainly to paints, then a significant amount of the sample weight would be coming from the pigments. So you might need slightly larger samples, but 10 micrograms, 20 micrograms usually gives a good result.
Okay, next question is also for you. How can you match the results with the ESCAPE program all the time if you can use different chromatographic conditions?
If the person is asking a question about different GC systems, columns, and things like that, that's where retention index is helpful. So if the user is, let's say someone wants to take advantage of the ESCAPE database and the ESCAPE system, if they use the same column that we use, which is a standard DB5MS column, as long as they can calibrate the system using a mixture of linear alkanes from C7 to C40, then they can calculate retention indices that are essentially the same retention indices as what any of the users around the world would have obtained. So that helps to remove the much of the instrument-specific variability in the chromatographic results.
Okay, next question is for Rogine. What exactly in the EGA is used to determine the optimal pyrolysis temperature?
Okay, so whenever you perform your EGA, of course, you want to have it from a lower temperature a little bit all the way to higher. For example, say you program your furnace from 100 to 700 C, then compounds start evolving. So at that point, you can start analyzing your EGA using the F-Surge EGA-MS and also extracted ion, so EIC chromatogram, and then identify the appropriate thermal zone. For example, in the cases that we showed, I could show that here on a slide. For example, in this case, on a single shot, you see how the more intense peak that is coming off around 550 or 600 C. So that will be the place you want to have your flash pyrolysis done. So if you would have chosen 400, you would not really create the fragmentation of the polymer. So you want to break down the polymer into fragmentation to a proper temperature from your EGA.
Okay, the next question looks like it's for Terry Ramus. In double shot, does the pyrolysis step stick to the standard calibration of the reaction conditions assumed by the major databases?
Yes, the second step, or the flash pyrolysis step in the double shot, is exactly the same as the flash pyrolysis performed in a single shot. And the key is that prior to that, we've run an EGA experiment in which we've been able to find the correct temperatures for the first and second shot, such that we are just removing the volatiles, the thermally extractable small molecules in the first step, and retaining the polymer information for the second step, flash pyrolysis. So in that case, the pyrolysates of the second step of a double shot, that flash pyrolysis will be the same as the single shot. It's just that there won't be any additives or small molecules in the way. So the libraries can be used in either of those flash pyrolysis modes for identification and characterization.
Okay, this next question is also for you, Terry. What would be some of the maintenance for the Pyrolyzer-GC MS?
The most important thing regarding maintenance is to use the correct sample size criteria. Dr. Schilling alluded to that exactly. And depending on, as he mentioned, the amount of organic material present, those numbers can change a little bit, maybe up to 200 micrograms on the upper end. And so if you follow that sort of use, then periodically, maybe once a quarter would be typical. And it will, of course, depend somewhat on the number of samples run. The maintenance procedure is to remove the quartz tube and either replace or flame clean, and then there is a ferrule and a needle that you replace. Those are the only consumable items. Once that is put back together, you have a brand new pathway from the point that the sample drops into the system up to the point that the pyrolysates or other analytes enter into the GC inlet. The GC inlet remains typically very clean in this technique because the residual materials are retained in the cup and are removed. So those would be the maintenance procedures that you would have on top of your normal expected GCMS procedures.
Terry, may I add one thing?
Of course.
One thing that we found is that if you were to, once you finish using the instrument, that you put the instrument in standby, so reduce the furnace temperature down to a couple of 100 degrees, same with the interface, and same with the GC inlet. The septum on the inlet, the O-ring on the inlet, and the O-ring on the furnace tube last much, much longer in between cleanings and maintenance.
Absolutely. Excellent, excellent practice.
Okay, the next question is for Rogine. Besides material characterization, what are some other applications of this technique?
So this technique really has very broad application in different, industries. For paint industry specifically, you could use it for contamination analysis, failure analysis, a good versus bad, for example, deformulation, or even the reverse engineer, so any type of competitive deformulation on paint and coating samples. You could also perform degradation analysis because EGA is very similar to kind of like a TGA type analysis. So as also mentioned, besides flash pyrolysis, this is a multi-mode furnace, which allows you to actually perform multiple analyses. So you could do thermal desorption that are like thermally extracting all the volatiles and also performing flash pyrolysis at the same time. Using F-Search, I can also mention that you could create your own user library. And a lot of our customers, they create their own user library. They run standards and references and save that maybe as a good sample, and then they could compare it to the other samples that are submitted or perform failure analysis to kind of identify, for example, some additives were found in sample A, but they were not found in sample B, just as an example. And of course, we talked about hard cutting, how they can perform reverse engineering because you can really, in detail orientation, you can analyze the composition of your sample. So these are the main categories of the application, I would say, they can use this system for.
Okay, next question is also for you. What temperature does the furnace operate at?
So the furnace goes from 40 C to 1050 C. And it really depends on, after you run your EGA, your evolved gas analysis, you have to figure out the optimal. So if you want to do thermal desorption, you have to figure out the optimal thermal desorption or the flash pyrolysis. But in flash pyrolysis, it will be one single set point for polymers. But in a double shot, for example, you program it from 100 to 250 C, for example, and then you'll do another shot for flash pyrolysis at 650 or 550 C. So it really depending on your EGA thermogram.
Okay, Terry, what steps to do when a sample is not listed or confirmed in any database?
Okay. And of course that happens. If the type of experiment you're doing focuses on the volatile components, as an example, the early eluting, the small molecule components, you would have, of course, full use of the NIST library, other GCMS libraries, as well as the Frontier library specific to polymers. So, of course, you'd go through all of those libraries, along with, for example, something like the ESCAPE system. If you then got to the point where you absolutely weren't able to identify something, you would be really back to where you are with any GCMS technique in terms of looking at a fundamental elucidation of structure from the spectra. If, on the other hand, you're looking at the actual pyrolysis, flash pyrolysis, and you're wondering what polymer it might be, then again, of course, you use the libraries that are available to you to search. And if you don't have any hits, then a couple things could be the case. One is it could be a novel polymer, something that is very unusual. More typically, it might be a mixture, either a blend or a copolymer that has an unusual combination. So what we do next then is we look at the individual pyrolysates, and we see, actually, as Dr. Schilling was showing here in his very organized way, we see which pyrolysates fit with particular classes of polymers, and use that to give us a final interpretation.
Okay, this next one is also for you. What about some compounds that may decompose at high temperatures? Is there a way to get around that?
So the system does, all of the analysis does take place in helium, so obviously it minimizes that as much as you can. Fundamentally, if the molecule is going to fall apart at a certain temperature, then that would, of course, take place here as well. If we're going to do a small molecule thermal extraction, we will start at a lower temperature and ramp up to our ultimate temperature so that we can remove the volatile compounds at the lowest possible temperature that they become volatile to minimize thermal degradation. If we're looking at a polymer and it falls apart, if you will, that's actually pyrolysis taking place. So that would actually be the information that we would be looking for characterizing, probably in this case, like maybe a polycaprolactone, something that falls apart at a very low temperature.
Okay, great. Well, that is all the time we have for questions today. Please join me in thanking Rogine Belganet, Dr. Terry Ramus, and Dr. Michael Schilling for their presentation, as well as our sponsor, Frontier Lab. If you have any additional questions or comments, please don't hesitate to click the Email Us button on the console. As you exit today's webinar, please take a couple of minutes to complete the survey. We strongly welcome your detailed comments. Please visit webinars.pcimag.com for the archives of this presentation, as well as information about our upcoming events. We appreciate your time and hope you have found this webinar to be a valuable experience.